Okay, so let us start. So first remind you the master formula we derived before for path integral is that if we consider time-ordered anything, okay, so let me just call it x, will be, say, some product of operators. And then this can be written as, in the path integral form, say d phi, and then, so x is just going to here, and then you have is, okay? And then divided by d phi, just without x, just is, okay? So this is the master formula we derived before, which applies to any theory, okay? In principle, any theory and any x you want, okay? And so since inside this x should always be time ordered, okay? So this t means time ordered. So now we can apply this to interacting theory. So for interacting theory, we have S, we write S, so the action to be the free theory action plus the interaction part, okay? And the interaction part in turn can be written as, say, the integration over the interaction part of the Lagrangian density, and it's also the same as the minus the interacting part of the Hamiltonian integrated over time. Okay, so the reason for this simple relation is because we assume the interacting part does not contain time derivatives. So the potential, so essentially, interacting part corresponding to a potential in your Lagrangian density, and then in the Hamiltonian they just differ by a minus sign. Okay. So now we can just apply this to this case. Okay. So let's see. So we can just write this object. So now we can write it as. So also come here. So our goal is that we assume the Si is small compared to S0 because we cannot solve this theory exactly. And so what we are going to do is we want to treat this I to be small and expand in the coefficient in Si. Okay, so example of Si is this lambda phi 4, which we wrote down before. Okay. So for this purpose, then we can just write this more explicitly as the d phi. Then you have x. Then you have is0. Then expression isi. Okay. Then divided by d phi. Expression is0. isi. Okay. And then now, so we can now treat this as the integrand for the so this is the integration for the free theory. Okay, so now we can interpret this just as an integrand for the free theory as some, say, x prime. So x times the expression isi as another x for the free theory, and similarly here. Okay, so we can write this as follows. So we can write this as now in free theory. So upstairs should corresponding to Z0. Let me just not worry about it at the moment. So now you can write it as then time ordered x expression isi 0. Now this is in free theory, so I put a subscript 0 here, means in free theory. Okay. So in writing from here to here. So upstairs we interpret it as a correlation function in the free series. So here we should also divide by in order to write in terms of the expectation value in the free. So 0 here is the free series vacuum. So in writing the upstairs in this form, we should divide this by a path integral just with the expression I as 0. But since upstairs and downstairs we need to divide by the same path integral, they just cancel. Okay, so I can just directly write down as the ratio of these two correlation functions. Okay, and so now this is a very nice form. Okay. Because the so this is a let me call this equation star. So this is a star is the exact expression. Okay. Which writes correlation function of an interacting theory in terms of lots of free series. Okay. So now these are just some correlation functions in the free series. So both upstairs and downstairs, they can, in principle, evaluate it as we discussed before in free series. Yes?
So I'm a little confused. What is there to time order for the phase for e to the I with the interaction?
Right. As we discussed before, whenever you see time order the exponential, you should always expand the exponential in power series, and then you just have a bunch of factors and you just time order them. Other questions? Okay. So and this is precisely the expression which derived in Paskin. Okay, so this is the so this equation is the 4.31 of Paskin and Schroeder. Which they derived using the interaction picture. Okay, so we see that for the path integral, to derive this equation using path integral is just trivial. Okay, essentially you just split the exponential for the full series into that of the free series and the interacting part, and then you automatically derive this equation. Okay, so once you have understood how path integral works, and then derive this equation become trivial. And so this is actually general. Later the same expression we will be able to apply it for, say, when we include fermions and also photons, etc. Okay. And now we will evaluate this guy's union perturbation theory. Okay, so we will expand star in power series of Si. Okay, we treat Si as small and just expanded in power series. So more explicitly, say we consider Gn. So this Gn for the full series. So let me call this Gn. Just say this is some endpoint function. Okay, so this is Gn, and then we can just more explicitly we can just write Gn as so at the zeroth order you just have Tx 0, okay, upstairs. And the next order would be I dt, say 0 t x hi. So I have expanded to the first order in SI. When I expand SI, then become dt times hi with a minus sign. So I just write it in terms like that. Okay. And so remember here you need to time order them together because both of them are in the same integrand. Okay, so we need to time order them together, and etc. Okay, so this is upstairs, and downstairs you just expand this guy. So essentially you have 1 minus I dt. Then you time order the Hamiltonian. Interacting part of the Hamiltonian, and then plus higher order. Okay, so you just now essentially do the Taylor series expansion, and yeah, and the first. So you always assume the interacting part is small, so you can actually Taylor expand the downstairs also. So this will be reduced to say the first order. So the 0th order just give you the free series endpoint function. Okay, so I denote now with a subscript 0 means the free series correlation function. Okay, and then yeah, and then you can add the rest, etc. Okay. Okay, so the higher order are the perturbations. Okay. Good. Any questions on this? Yeah, actually, for later purpose, let me just write one more term, just explicitly. Let me just write it. So I bring this up. So when I bring this up, and then this become I 0 tx 0, then times dt 0 thi. Thi 0. So this is this term we bring up, and then multiply that term, that give you that. And then there's another first order term. It's given by I dt 0 t x hi 0. And then so these are the full first order terms. Okay, so these are the full first order terms, which is the correction to the free series endpoint functions, and we need to evaluate those quantities. And all those quantities can be just evaluated using the Wick theorem, because we know how to, because all correlation functions in free series just can be evaluated using Wick theorem. You just use the Wick theorem over and over. Okay. So any questions on this? So now we will develop techniques to evaluate such kind of series. Okay. Still, even though this is not too difficult to do now, but still, when you do it in practice, it's pretty tedious. So still, worth making effort to actually simplify the process. Okay, simplify the process, and the technique to simplify is called the Feynman diagrams. Okay, so now we will consider. So far, those equations apply for any series, any kind of interaction. Okay, so now let's work on for a specific case. So let's consider Li equal to minus lambda divided by 4 factorial, 5 to the power 4. Okay, so it means that Hi would be, you integrate over. So Hi, yeah, so, yeah, anyway, yeah, the others you can just directly write from here, okay? So let's consider this case, okay? And to be specific, And now also let's consider just in the simplest correlation function, let's just consider 2-point function. Okay, let's just consider 2-point function, G2. So 2-point function is also the Feynman function, but now this is a Feynman function in the interacting theory. Okay, and so now this is in the so now we have two. So imagine we have two coordinates, and then it's equal to now. So let's consider this. Okay. So now let's consider the Feynman function at the in the full theory. Okay. And now we can just now apply this equation. So let's try to let us try to calculate to the next order. So the zeroth order, just given by the free theory, 2-point function. So by translation symmetry, it's always a function of x1 minus x2. Okay, so this does not depend on whether it's in the free theory or interacting theory. And now let's just plug in here. Okay, let's just plug in here. So hi is integration of this over a 3-dimensional spatial, and then combine this become just 4-dimensional space-time integrals. Okay, so then you just get the so this term become plus I lambda divided by 4 factorial. So we will assume this lambda is small. Okay, so that we can expand this lambda. So, and this term just again is the free theory correlation function. So we just have GF, again 0, x1 minus x2. Okay, and then times. Okay, my board is a little bit so we have to go to here. Times, then you have d4x, then 0t, and 5 to the power 4x here. Okay, so this is multiplied with that. Okay, so that's the second term. And the third term is minus I lambda to the 4 factorial. You have d4x. You have 0t. Then you have to combine them together. Okay, so this is phi x1, phi x2, and then phi to the power 4x, and this x is integrated over. Okay, and then 0. Okay, and so this is all time ordered, and then the rest is all the time lambda squared. Rest lambda squared. Okay. Good. Any questions on this? So yeah. So let me just make a quick remark. So in the end, so just note, can be so. Yeah. So here, even though we only write down the first order term, but you can continue. Okay. So all terms in the expansion can be evaluated by repeatedly apply the Rick theorem. So they're all, any such kind of functions, they're all factorized into 2-point functions. And the 2-point functions are essentially just given by GF0. Okay, just the GF0 free theory 2-point functions. Okay, so the final result always have the form finally dot always have the form sum over product of GF zeros. Okay, and the plus some integration. Okay, so sum of the plus portable integrations. Okay, so the structure in general, the structure is pretty simple. They all just reduce to the product of those 2-point functions. Okay. So now let's just, as example, let's just evaluate these two pieces. Okay, evaluate these two pieces. So let's continue. So we find that GF x1 minus x2. Yeah, so GF is the same as G2. Okay, so for 2-point function, this is just the Feynman function for the interacting theory. So the leading term is just GF0. Okay. And then now let's evaluate this term. Now evaluate this. So this is all phi contracted on the same point. Okay, so there are 4 phi's. We can just contract them. Okay, with the within themselves. So we essentially get the so you have GF, and then the next term is I 4 factorial, I lambda 4 factorial, and then you have GF0. So x12. So let me use x12 to denote x1 minus x2, just to save a little bit effort. And then we have this integration over d4x, and then let's evaluate this. So this just reduced to 2 Feynman propagators, but both of them have 0. So essentially, you just have GF0, 0 is x minus x. Okay, so we just get that. Okay, x minus x. Okay, so let me just write one of them so that you. Okay, but we are actually missing some factors because we have 4 phi's. So when you contract the 4 phi's, there are 3 different ways to group them. Okay, so we should have a factor of 3. There are 3 different ways to group 4 phi's into 2 groups. Then we have a factor of 3. Okay. Okay. So now let's look at this term. So this term now we have to contract 6 phi's. Okay, so phi x1, phi x2, and then there are 4 phi's here. So we need to contract 6 phi's. So we can have 2 possible patterns. Is that these 2 phi's contract with themselves. Okay, these 2 phi's, this phi x1 and phi x2 contract with themselves, and then 4 phi's will have to contract with among themselves. Or phi x1, if phi x1 contract with one of the phi here, then phi x2 also have to contract with one of the phi here. Okay, so you have 2 possible patterns for contraction. Okay, so the first one is simple. So let's just first contract phi x1 and phi x2. So again, so we have minus I minus I lambda divided by 4 factorial. So when we contract x1, x2, then we just get GF0 x12. And then we contract phi form themselves. That's what we did before. It's the same thing as above. So we just get a factor of 3, d4x, and then GF0, we value at 0 square. Okay? Just the same as this. Okay? But then the other term, phi contract with this. So each of these x1 and x2 contract with here. Okay. So in this case, so let's imagine this contract with them. Then there are 4 possibilities. So after this contract with one of them, this contract of that, then I have 3 possibilities. So you have 4 times 3 combinatorial factors. Okay, so you have I lambda 4 factorial. Then you have 4 times 3. Then you have d4x. Then we have here, we have g4, 0, x minus x1. So x1 minus x, it doesn't matter. And gf 0, x2 minus x. And then the last one just contract with itself, just again, gf 0, 0. Okay? Times. And then all the lambda squared. Okay? So these are the explicit expressions. Okay, so these are the explicit expressions. So now you can actually notice that these 2 terms actually are the same, right? Okay. So these 2 terms actually are identical, and they just differ by a sign. So actually they cancel. Okay. So this cancel. So we just left with that, and then this term. Okay, we just with this term. Okay. So this procedure can actually be represented diagrammatically. Okay, be represented diagrammatically, and I will just introduce a single line. Just introduce a single line for GF, say x and y, for GF 0, x minus y. Okay, so I will just represent the line like that. Okay. So if I use that, and then we can write them in the diagrammatic form, then the first term is just x1, x2. Okay. And now the second term would be if 3 multiply 4 factorial, so this is like I lambda divided by 8. Okay. And then you have x1 times x1, x2, then times this contracted with itself. And so you have 2 propagator, one is contracted like that, and one is contracted like that. Okay? And this point is x. Okay? So you have x, but they all contract with itself, so it's x minus x for this one, and x minus x for that one. Okay? And similarly, of course, this is identical to that. It's I lambda divided by 8. So this is times. So x1, x2. X. Okay? And then the last one, so this one corresponding to, say, now this is 12 divided by 24. This is minus I 2 lambda. Okay, and lambda divided by 2. So now, so x1 is to x, and x2 to x. And then you have something like this. x1, x2. Okay, so this here is x. So x1, x, x2, x, and then x2 itself. Okay, and then you have all the lambda squared term. So this again, these 2 terms, as we already said, these 2 terms cancel, and then you just get these 2 terms. Okay, just get these 2 terms. Okay, just 2 terms. And we see that each factor of hi or each factor of si you bring down. Okay, so each factor of hi or each factor of you bring down corresponding to an interacting vertex like this. Okay, corresponding to interacting vertex like this. You have 4 legs or 5s. Okay, and so we call this interacting vertex. Okay. Okay, so there. Okay. So in practice, it's actually much easier to just draw the diagram first, and then from the diagram to write down the analytic expression. Because the diagram is much more intuitive. Essentially, what's happening here, whatever terms here, you just find all possible way to contract them. And diagrammatically, we can just do it diagrammatically through all possible way to contract them. That's much easier to do by drawing a diagram than by do the counting. Okay, by do the counting. So in practice, much easier to draw the diagram first. You just draw all possible diagrams, okay? And then from diagram, write down the expressions. Okay. So those diagrams are just called the Feynman diagrams. Okay. So we just draw possible diagrams, and then from the diagrams we write down the expression. That's called the Feynman rules. Okay. I give you a diagram, then there's a rule which converts them into such kind of expression. Okay. We can convert them into such kind of expression. Okay. So now let's give you an example. Okay. So now let's give you an example. So now let's look at the example in the second order. Okay, let's look at the example in the second order. So let's consider, order lambda square example. So the lambda square, there are many terms. Okay, so one of the term. The one of the term is just to say you now have hi square here. Okay, you also have downstairs, etc. There are many terms, but one of the term, right. Yeah, let me just say here. So one of the term is just x, and then you have hi square here. Okay, this is one of the term. They also have other terms. So let's now look at just that term. Okay, as example. So at the lambda square example, there's a term like this. 1 factorial count when you expand this to the second order, then there's 1/2, and then you have minus I lambda 4 factorial square, because now this coefficient also expand to second order, and then you have d4x, d4y, x1, x2, by 4x. By 4y, 0. Okay, so now one of the term is like this. Okay. So later we don't even need to write down such a term. We just immediately write down all the diagram. Okay, just here to help you to understand the process. Let's just say let's look at this particular term. So now let's try to write down all possible contractions by just using diagrams, okay? Just by using diagrams. So now we have x1, x2, and the 4x and the 4y's. Okay, so essentially you have something like this. You have x1, you have x2. So these are the two external points, okay? And then now you have 4 phi's coming from x, and the 4 phi's come from y. Okay, so we need to find all possible ways to connect them. Okay, we find all possible ways to connect them. Okay, so that's the goal. Okay. So So here are the all possible ways. So first, there are actually 5 in equivalent way. Okay. So let me just write them down. So the first one is you just connect one of them to x, and one of them to x. One of the x. Let me just draw them down. Okay. So one of them is the following. So you take one of the x. So there are 5 of them. So let me write equal sign here. So each one of them, let me give a label. So for later use. So here you can have say x1 and x2. Then they can connect to x. And then x can connect to y. Okay, so this is one of them. Okay. And the second one possibility is you just x1 connect to x, and the x2 connect to y. And now there are 3. Now there are 3 between x and y we have to connect. So we can have something like that. Okay, so this is the second. So the third and the third way is you connect x1 to x2 itself, and then times, and then you have to connect x and y. So there are 4 of them. Just connect x and y like this. You can connect them like this, and or you connect x1, x2 itself, and then you again have to connect with x and y. But you can connect and y not just between x and y. You can also have that. So sum of x is contracted y, and sum of x is contracted with itself. Okay. And or you have the last possibility. So you have x1, x2, but then the x just contract with itself, and the y also contract with itself. Okay. So any questions on this? So these are essentially all possible contractions you can have between them. Okay, we just draw them diagrams. But now we also have to calculate so we also have to find the combinatorial factors between them. Okay, we also have to find the combinatorial factors between them. Okay, so now let's try to work out the combinatorial factors. Okay, so let me just give you an example. Give you some examples, and then the rest I will just write down the answer because it just takes too much time to do all the examples one by one. Okay. So let's do this one as an example. Okay. So yeah, let me just erase here. I may need space here. So here, actually, there are 2 possible diagrams. I can have x1, x2 connect to x. I can also have x1, x2 connect to y. Okay, and so this because x and y are symmetric, so I only draw one of them. Okay, so that means there's a factor of 2. I can either connect to x or connect to y. So I have 1/2. So let me also copy this lambda 4 factorial square. And then I have a 2 factor can either connect xy, x2 can either connect to x or connect to y. Okay, so x1 have 4 possibilities to connect to x, and x2 have 3 possibilities to connect to x, and then the remaining phi x then have 4 possibilities to connect to y, and the other remaining phi x have 3 possibilities to connect to y. Okay, so essentially that's your prefactors, combinatorial factors, and so if you worked it out, so that's give you minus lambda square 1/2 square. Okay. Yes.
Why were there 4? So after we connect x1 and x2 to x, why were there 4 remaining?
Yeah, it's because the now you have 2 phi remaining, for 2 phi x remaining. So 2 phi x remaining have to connect with y. So the first phi will have 4 possibilities to connect y because there are 4 y's there. So that's this factor of 4, and then the other phi x have 3 possibilities to connect to y, and so that's factor of 3. And once you do that, then there's y just have to connect with itself. Yes.
We have a diagram x1 to x to y, y to x2, and x loop and y loop.
Sorry, which one? Say it again.
x1 to x.
X1 to x.
And then one loop at x.
Yeah.
X to y.
Yeah.
One loop at y. And y to x2.
And y to x2.
I think we didn't include that.
Yeah, let me see. Yes, I should also have a diagram like this. Yeah, it's possible. I think I just forgot it. Let me see. Do I have something like this? No, actually. Yeah, then I forgot it. Good. This diagram is here. Okay, so this is B prime. Thank you. Thank you. So we can also have that. Okay, so we can also. Yeah, here it's really for the illustration. I should claim at the beginning I didn't aim for completeness, and just for illustration, because if we try to be too complete, then that may take too much time. Okay, good. This is also a possibility. Yeah, yes, good job. And so now let's look at this one. Okay, now let's look at this one. So again, let's copy this 1/2 minus I divided by 4 factorial square. Okay, and then the combinatorial factors. Again, I can have the freedom. So x1 either connect to x or connect to y. That 2 diagram would be the same. Okay, and so I have 2 possibilities. Here I only draw one of them because I just flip them because x and y are symmetric. So I have a factor of 2. And then the x1 have 4 opportunities to connect with the 4 of x, and x2 have 4 possibilities to connect 4 of y, because x2 connect with y. So I have 2 factors, 4 and 4. Okay. Okay, and so after that, so phi x have 3 left, and phi y have 3 left. And then take one of the phi, then have 3 possibilities you can connect to y. And then the other one have 2. Okay, and then that's it. Okay, that's it. So that's all the possibilities. And if you work it out, so this gives you lambda square divided by 3 factorial. Okay, and then so as an exercise, you should work out this one yourself. Okay, and which I didn't work out, and but I did work out these ones. So these ones also give you as exercise. So this is minus 1/2 lambda square 4 factorial square times 4 times 3 times 2 equal to minus 1/2 lambda square divided by 4 factorial. And so this one is the, again, minus 1/2 lambda square 4 factorial square times 2 times 3 times 2 times 3. So that gives you minus lambda square divided by 16. So this final one is minus 1/2 lambda square divided by 4 factorial square times 3 square, and then given by minus lambda square divided by 2, 1/8 square. Okay. Good. So I write them down just for you to check yourself later. Okay. So I urge you just as an exercise for yourself to write them down later yourself. Okay. To do this exercise later yourself. So here we can already observe some patterns. Okay. So here we can observe some patterns. And so you can do this for each individual diagrams. Okay, you can do this individual diagram. But if you try to count this way, okay, if you try to count this way as we are doing here, even though it's not difficult to do, okay, but it's still tedious. Okay, it's still tedious. But each diagram have to count factor 4, 3, etc. Okay, so it'd be nice to find a better trick. Okay, so now there's a better way to do it. Okay, so the better way to do it. So better trick. So if I notice the following. So when you go to the lambda nth order, so there's always there's an n factorial coming from expanding the exponential. Okay. So because we are expanding the exponential and okay, so there's always a factor of a factorial come from the expanding of. So now, at the nth order, yeah, I think I erased my vertex. So at the nth order, you have n factorial from exponential, but you also have n vertices. Okay, because each power. Each lambda comes with a factor of these vertices. Okay? So now, when you permute all these n, so when you permute the n interacting vertices, okay, and you also get the factor of n factorial, okay, because you can, okay, because they're all symmetric, okay, they're all symmetric doing the contraction, and if you have one way to contract, and then you can have another way to contract by permuting all these different vertices, okay. So then these two factors cancel. Okay, these two factors also modular symmetries in permuting vertices. Okay, if there are symmetries in permuting vertices, okay, and then of course you don't get n factorials because some of the permutation give you the same diagram, okay, and so the modular symmetries in permuting vertices, and you have this n factorial, okay. So this is the first observation. So the second observation is that for each vertex, which you have minus I lambda divided by 4 factorial phi 4, okay. So if each phi in this phi 4 contracts differently, contracts differently. So all these 4 phis are symmetric with each other. Okay, there's no not any phi which is special. But if they but if each phi contracts differently, then again you permute the phis. It should be the same. Okay, it should lead to that diagram should also be included. So that. And then you can permute phi permutation of 4 phi's, then leads to 4 factorial. Okay? So again, modular. So this 4 factorial again cancels with this 4 factorial. So the two 4 factorial cancel. Okay. Modular symmetries in permuting phi's coming from the same vertices, coming from the same vertex. Okay. Okay. Again, so if these two phi's are contracted the same, of course, when you permute them, you don't generate a new diagram. Okay, you don't generate a new ways. So now we have two different permutations. One is to permute the vertices, and the second is to permute the phi's within each vertex. Okay, within each vertex. So that means both this n factorial and this 4 factorial, they cancel. Okay. So we can forget. So this means forget about the n factorial factor from exponential. And we also forget about this 1 over 4 factorial, and then treat each vertex minus I lambda. Okay, just coming from a factor of minus lambda. But then this way we overcount. Okay. So this way we overcount. And then we need to divide so we need to divide and then divide by symmetry factors. Okay. From permuting vertices and the legs. Okay. Yeah. Okay. So now let's go back to this diagram. Okay. So now let's go back to this diagram. So in this diagram, there's no symmetry between x and y. So there's no because x and y they're not symmetric. So we don't need to divide. So there's no symmetry factor associated with the permuting the vertices. But for the vertex come from the x, these two legs are symmetric. Okay. So there's a factor of 2, okay, permute them. And for this thing coming from y, again, there are 2 of them are symmetric. Okay? So that's why we divided by 2 symmetric factors, so this 1/2. Okay. And similarly from here, again, the x and the y, they are asymmetric because one is contracted with x1 and one is contracted with x2. So there's no symmetry factors from commuting the vertices, but between x and y there are 3 legs which are symmetric. Okay, when we permute these 3 legs, And then we have 3 factorials. Okay, so we have 3 factorials. Okay, so and similarly, leave as exercise for you to do the other diagrams. Okay, to do the other diagrams. So now we are ready to just to write down our rule. Okay, so now we have drawn the diagrams. And now we can use the diagram to write down expressions. Okay, so the rules of writing down expression from diagrams are called the Feynman rules. Okay. Feynman rules. So here is the Feynman rules. So okay, so here is the Feynman rules, which we can. So these are all very intuitive. Okay. So for each external point, so here we have some external point. Okay. So each external point you associate with a line, okay? So here is the, say for example, x1, and then you just associate with a factor of 1. But there's always a line coming out of the external point because you have to contract with that one, okay? And then for each propagator, so the propagator we already wrote down. You just have, say, you have 2 endpoints, then that's corresponding to GF0, x minus y. Okay? So each such a propagator, you can just write down a factor corresponding to GFy. And then for each vertex, I think I can erase them. So for each vertex, so has point x, so you associate with lambda and the integration over x. Okay? And then you, the last step, you divide by symmetry factors. Okay, symmetry factors for diagram. So so you just draw all possible diagrams using this kind of rule. So for each propagator, you have a line, and then you have vertices. And now, so now from each diagram, by applying this rule, we can also write down the analytic expression. Okay, we can write down analytic expression. Any questions on this? So exercise for yourself to write down analytic expression for each of them. Okay, so yeah, let me give you an example. So for B, so you should, as an exercise, you should try to do yourself for each of them. Let me just give you one example. For B, and then you have first the symmetric factors, lambda squared divided by 3 factorial. And then you have d4x, d4y come from these 2 vertices. Okay? Yeah, I should just write it like this. Sorry. I should, yeah, let me just strictly follow this rule. Okay. So we have 2 vertices. So each vertex we have I lambda square. Then you have d4x and the d4y. And then for each propagator, we associate this, and then we have GF 0, x minus y, then cube. And then finally, we divide by symmetry factors because there's 3 permutation of them. So we divide by 3. Okay? So this is the analytic expression corresponding to that diagram. Okay. So now just later, you don't even have to write down such an expression in the top line I wrote down there. You just at each order, you have certain number of external points, and then just have number of vertices come from nth order. You just have n vertices. You just try to connect all possible lines between them. Okay, and then that's all possible contributions. Okay. Good. So this is the Feynman rule in coordinate space. It's also convenient to go to the momentum space. Okay. So it's also convenient to go to momentum space. So to go to momentum space, then we can define the Fourier transform. Okay, so let's define the Fourier transform. So suppose we have an endpoint function. Okay, suppose we have an endpoint function Gn suppose we have an endpoint function x1, xn, okay? So so this is just the standard Fourier transform. So because of the translation symmetry, okay, so we expect all the p's must be conserved, okay? Just from the conservation, I will derive it, but you should also be able to expect on the general ground from the translation symmetry. So we expect that there must be a factor of the momentum conservation coming from here, okay? And then we call that coefficient GMP. Okay. So the momentum. So our convention is that for momentum space correlation functions, we defined without this factor. Okay. Without this factor. Yes.
For the Feynman rules, isn't there also shouldn't we also restrict to connected diagrams?
Oh yeah. We will talk about that later. Yeah.
Okay.
We'll talk about that later. Good. Yeah. So here I'm just talk about the general rule, and then we will talk about the more fine points, how to enumerate all possible diagrams. Yeah.
Thank you.
Okay. So when we define the momentum space correlation functions, we extract out this factor. Okay. So the reason for to extract this is from the momentum conservation. So to see this, okay, to see that there's a factor like this, it's very easy. Okay, so because from the translation symmetry, so the same argument that the 2-point function, so x1, x2, should only be a function of x1 minus x2. So for the endpoint function from the translation symmetry, so this you can just take one point to be the reference point. You can subtract, say, all coordinates by the value of xn. Okay. And then the last argument becomes 0. Okay, so you can choose one point as a reference point and subtract any other point from it, and that should be equivalent. Okay, because it doesn't matter where you choose the reference point. So here let's choose the reference point to be xn. So this should be equal to that. Okay. So now when you do a Fourier transform, So now when you do a Fourier transform, so you can easily convince yourself, okay? So when you do a Fourier transform of this object, when you plug this into here, okay, when you plug this into here, and then you get a delta function, okay? Okay, so so this is a simple exercise for yourself to do, okay? And so if you plug in here, you find that there's always a delta function. So now recall that the momentum space, the Feynman propagator for the free theory in the momentum space, if you say k, then it's given by minus I k squared plus m squared minus I epsilon. So now you have a line, but now it's labeled by momentum k, okay? Now it's labeled by momentum k. So this k denotes the flow of the direction of the momentum, okay, this arrow. Good, so now with this rule, you can easily write down what is the, now you can just translate right. Okay, so this is the one point and another point, and the third point. So let me just, in order to go to momentum space, let's just mention several points. So yeah, anyway, so here is one point, and then here is other point. And also now let's look at the vertex, okay? So at each vertex, we have integration. So suppose we have a vertex like this. So here is x, and this is contracted with y1, y2, y3, y4, okay? So let's imagine, so we have a vertex like this, these 4 phi's contracted with 4 different y's, okay? And then we will have expression at such a vertex, then we will have expression like this, gf0, x minus y1, gf0, x minus y2, and gf0, x minus y3, gf0, x minus y4, okay? Okay. And now again, so now when you plug in the expression, okay? So now if you plug in the expression, so I will not write all the lines here. I think you will just see the basic idea. So this one, if you write, now let's write each of them in terms of momentum space. Okay, so this, if you write in terms of momentum space, then you get a d4 k1, expansion I k1 times x minus y1, then gf0 k1. Okay, and similarly for that, and for that, okay? So now you have, and now these have expansion ik1, so these have expansion ik2, so these have expansion ik3x, and these have expansion ik4x. And there's no other x dependence, and then you have d4x here, okay? So what you get, then you just get a delta function. So you just get the delta function. So when you do that, when you go to momentum space, then you find that this should always be proportional. Okay? So that means momentum is conserved at each vertex. Okay? So if I draw, say K1 here, K2, Okay, 3. So I use the same convention for all of them. It doesn't matter whether you draw it outgoing or ingoing, but we draw the same convention for all of them, and then they should have to be then they should be proportional to a factor of this. Okay. And here it doesn't matter what is y1, okay, yi. So y1, y2, y3, y4. They can either be some external point or some other internal point. Okay. Yes.
G n of t object, the endpoint function in
Yeah.
space. Is that like, can you get that by writing expectation values of the momentum field operators, like pi of k1, pi of x1, pi of x2, or is that?
Yeah, you can. Yeah, you can.
And how would you do time ordering there? Because then.
Yeah, yeah. So this is strictly defined in terms of the. Yeah. So no, you cannot write that way in the sense that the not as a whole momentum. Yeah. Now you cannot that way. Yeah.
So you have to.
You really have to find the final expression and do the yeah. For the Weidmann function you can, not for the time ordered. Yeah. For the Weidmann function you can. Yeah. Okay, good. So now we can write down the momentum space Feynman rule. And we will not have time to do it, to do an example. Let me just write them down, and then we will look at the example next time. So so here is the rule to compute this Gn, P1, Pm. Okay, we use the following rule. So first, for each external point, and now you just can associate, say, a momentum, okay, with respect to that momentum, and you can associate with a factor 1, and then you draw a line, okay, still draw a line. But now you associate the momentum with this line, okay? Because when you Fourier transform this line, you will have momentum. And for each propagator, again, the propagator is given by this. So now you have a momentum. And then this is given by the momentum space p squared plus m squared minus I epsilon. And then now for each vertex, you have a factor of I lambda, and then you impose momentum conservation. Okay, at each vertex. Okay. So now remember, when we do a Fourier transform, each propagator, each line will have a momentum integration. Okay, because the each one of them is integrated over momentum. Okay, so each one of them is associated with a momentum integration. And some of those momentum integration can be get rid of by impose the delta function at the vertex. Okay, so you can get rid of some of them, and by momentum conservation at the vertex using the delta functions. So but now you will have, say, a number of them left. Okay, so then you need to integrate over each undetermined momentum. Okay, so each undetermined momentum, you need to integrate with this factor. Okay, and then the same thing you need to divide by symmetry factor. So symmetry factor is the same in coordinate or in momentum space. Okay. Okay, so this is the way which you can write down the momentum space expression for each diagram. Okay, momentum space expression for each diagram. Actually, maybe we still have some time. So we have a couple minutes. So we can just do this example. Okay. So this example, let's see what it looks like in momentum space. Okay. So in momentum space, we just could have erased the diagram. So this diagram looks like this. In coordinate space, we have x1, x2, and x and y. Okay. So now when we go to momentum space, we just put the diagram is the same. Just now we label the momentum. Okay. So we have the external line here, external point here. So here I have a momentum p1. Here I have momentum p2. Okay. So now let's just call say this k1, k2. You can assign momentum direction as you want. Okay, say k3. Okay. So now we need to impose momentum conservation. So momentum flow like that. So that means that the p1 should be equal to k1 plus k2 plus k3. Okay. From the momentum conservation at this vertex. And for momentum conservation at this vertex, they all go away from this vertex. And then in this case, then the P2 will be minus K1 plus K2 plus K3. Okay? So that means actually P2 should be equal to minus P1. So this makes perfect sense because here preserves momentum. So for momentum conservation, if you have P1 here you should also have P1. Okay, so P2 I draw with selective sign, and so we have lactive P1. Okay. So and now we can so using this simplified notation, then we can draw a diagram like this. Okay, so here is P. So let's call this K1. K2, and then this K3 can be solved in terms of the K1, K2. So this is just the P minus K1, K2. Okay? So this is the P minus K1, K2. So now you can just write down the momentum space expression. So we have minus I lambda. We have two vertex. We have 2 minus lambda square. Then we have 2 undetermined momentum, K1, K2. Because P1, this P should be external momentum should be fixed. Okay, so we have K1 and the K2, and then we just write down each propagator. Okay, so we just write down each propagator. So we just have minus I K1 square plus m square minus I epsilon corresponding to this one. Then I have minus I K1 K2 square plus m square minus I epsilon times minus I P minus K1 K2 square plus m square minus I epsilon. Okay? And then these other depend on the K. And then we have 2 factors. So this times these 2 external factors. So this is minus, they have the same momentum. So we just have P square plus m square minus epsilon squared. Okay? And then we divide it by 3 factorial, corresponding to the symmetry factors. Okay, that's it. So this is the expression for this diagram in momentum space. Okay? momentum space. Okay, so let's stop here.